Hello Bobcats. In this video we're going to talk about molecular geometry. And it's based on what's called the VSEPR theory, which stands for valence shell electron pair repulsion, where electrons will arrange themselves to minimize repulsion. In other words, they will get in angles as far away from each other to minimize the amount of repulsion that occurs. In this case we're going to look at what's called electron geometry, so that's the geometry of electrons, and then molecular geometry, which just looks at the geometry of the molecule due to bonds. We're also going to talk about hybridization a little bit, bond angles, and then we're going to draw dot structures. So here we're going to go ahead and get started. First we're going to start with beryllium dichloride, and so it's going to be a beryllium in the center with the chlorine and the chlorine on the outside. Now we'll notice that in this case beryllium only needed 4 valence electrons. It's one of the exceptions, and so we have the 4 valence electrons, or the 4 electrons around the beryllium. And we notice here when we just look at the central shape, the central element in a molecule, we have as far as electron domains, we have 2 electron domains, and then bonding domains, 2 bonding domains, and then there are no or 0 electron lone pairs. Now for electron geometry, that means that from this angle, from this bond to that bond, that angle there is as far apart as it can be, and it's a linear compound. And since we're only looking at bonds, since the bond domains and electron domains equal each other, it has a molecular shape that is also a linear molecular shape. Now the hybridization is the bonds have to hybridize, so you have S and P, or S2, so that would be an SP hybridization, and then it's a 180-degree bond angle from this bond to that bond, so it's a linear compound. So and that's there's just one linear type. So what I like to do is kind of divide this up, and so this linear compound, or the SP hybridized group, there's just only one type in that group. The next one we're going to start off with a boron trihydride, and so that's going to be a boron in the center, and then hydrogen, hydrogen, hydrogen. So we have 1, 2, 3 electron groups, 1, 2, 3 bonds. Whoops, I wrote 2, so I meant to write 3. Let me fix that. 3 electron groups and no lone pairs. And so this looks like a triangle, and so they call this trigonal planar because it's in a plane. And since the electron domains and bonding domains are the same, the shape of the molecule is trigonal planar. So we have an electron geometry and a molecular shape that are the same. This has got 3 domains around it, so this is going to be sp2 hybridized, and the angle from here to here is going to be 120 degrees. I'm going to take the arrows off of this just to show. Okay. Now there's another another shape that occurs with sp2 hybridized, and let's look at sulfur dioxide. And so we have a sulfur, double bond oxygen, single bond oxygen, lone pair. And I'm going to draw a little this would be kind of the orbital that the lone pairs exist in. And so we notice that this is not, I mean, as far as electron domains go, we have 1, that's a lone pair, that's 1, 2, 3 domains. The double bond is a domain, in other words, an area of where we find electrons. So that's 1, 2, 3 electron domains, but just 1, 2 bonding domains, and then we have an electron lone pair. So this is different, and what happens is every time you have a lone pair, it changes the shape of the molecule. As far as electron geometry goes, it stays the same because we're still looking at 3 electron domains. So that's going to be a trigonal, planar, electron geometry, but molecular shape depends on just the bonds, and since we only have 2 bonds, this shape is a bent shape. Bent, or sometimes you'll see angular. Okay? Because you'll notice there's a bent shape right here as far as the molecule goes. And it's still 1, 2, 3, so it's still sp2 hybridized. And in general, it's not exact, but in general, you lose some bond angle every time you have a lone pair. What happens is the lone pair pushes the bonds closer together, and so this bond angle here is 117.5. So in general, you lose 2.5 degrees of bond angle for every lone pair. That's not a steadfast rule, it's just a general pattern. Now, so that's it for sp2 hybridized group. So I'm going to draw a line here, and so that's sp2 hybridized. And so you can call this group the sp2 hybridized group, or you can call it the trigonal planar group. The next group we'll start out with methane, CH4, and the way that is that we have a carbon with a hydrogen and then a hydrogen. Now these hydrogens are in the same plane, and then I'm going to draw a wedge here showing that there's a hydrogen coming out of the plane, out of the paper, and then a dotted line to a hydrogen, meaning it's going back into the plane. It kind of looks like there's a tripod here with a pole going off the top, so like a camera type tripod with the camera here. Now we have 1, 2, 3, 4 electron domains, 1, 2, 3, 4 bonding domains, and no lone pairs around the central atom. Remember, we're looking at the central atom. And the name of this is tetrahedral. Tetra meaning 4, hedral meaning sides or faces. So tetrahedral, 4 sides or 4 faces. And if you can see this, there's a face between these here, a face between the ones in the back, a face between the ones on this side, so that's 3, and then a face here on the bottom. And since the electron domain and bonding domains are the same, the shape of the molecule is the same as electron geometry, tetrahedral. Now it's got 4, so it's sp3, 1, 2, 3, 4 hybridized. And the bond angles is 109.5 degrees between each bond. That's the furthest they can get away in a 3-dimensional space. The next one we're going to look at is ammonia, NH3. And this would be a nitrogen, and we'd have a hydrogen, then a hydrogen coming out of the plane, and then a hydrogen going back in the plane. This is a tripod right here, if you want to think of it that way. And then we have our lone pair up here. So when I look at this, we have 1, 2, 3, 4 electron domains, but only 1, 2, 3 bonding domains and 1 lone pair. Now as far as electron geometry goes, it still has 4 electron domains, so electron geometry is tetrahedral. But our shape is different because now we kind of look at it here without the electron lone pair, and so we just see this down here, and if you can put a base on the 3 down here, it looks like a trigonal pyramid. In other words, a pyramid with 3 sides, and we call that trigonal pyramidal. And it is also sp3 hybridized because it still has 1, 2, 3, 4 electron domains. But my bond angle, I've lost some bond angle for every time I add a lone pair, and it'll be 107 degrees. And then our last one in this group would be water, H2O. And so we have water with oxygen, hydrogen, hydrogen, lone pair here, lone pair here. Now this is hard to see here, but you kind of have to think of this lone pair going back and this one coming out. We have 4 electron domains, 1, 2, 3, 4. We have 2 bonding domains, and we have 2 lone pairs. Now because we still have 4 electron domains, it's still, electron geometry is tetrahedral. Oops. But its shape, molecular shape, we only look, remember we don't look at the lone pairs, we look at the bonds, and it's a bent shape. You can see that bent shape. So this is bent shape for the molecule, or angular. Some books will say angular. It's still sp3 hybridized, but we lost 2.5 degrees again, so it's 104.5 degree angles between the bonds. And I would think of this one as our, either you can call it the tetrahedral group or the sp3 hybridized group. So I am going to stop with this right here, and then I will add another video that includes the sp3 dehybridized and the sp3 d2 hybridized on the next video.